Okay, so I'll start now. Good evening and welcome to the problem solving session for week 9. I'm Shreya, the TA for this course, and today I'll be discussing few of the concepts that were discussed during week 9 lectures. But before that, as usual, I'm going to ask you if you have any doubts from the previous sessions, anything. O- Okay, so then I'm going to move on. Okay. So in during week 9, uh, Sir briefly discussed what problems would arise when we would have some model misspecification problems, like when the OLS assumptions would be violated. So one of the OLS assumptions uh, were that the error terms are uncorrelated. So under this assumption, the OLS estimates were the best linear unbiased estimators. But once the error terms become correlated, or there creeps in the problem of serial autocorrelation. That might happen because of some model misspecification. Maybe we have some omitted variables or we have some incorrect functional form. It could happen for various reasons. But whenever that happens, why is it important to detect what the consequences are if we use OLS estimation on a serially on errors where the error terms are actually correlated, and how can we solve that issue? So this was discussed, and also there was another phenomenon which is not exactly a model misspecification problem, but problems related to samples. That is multicollinearity problem, where one of the regressors become highly linearly dependent on uh, other regressors in the model. Then how can we detect those problems and what are the consequences and what could be the potential solution. So before moving on to the concept of autocorrelation, so whatever was discussed, it was mainly with respect to first order autocorrelation. That is, if we have a variable, this, let's say this is my regression equation, let's say, so we would have some uh, these errors epsilon t's would be autocorrelated. We would have something like this is something rho into epsilon t minus 1 plus ut, where this part will, these are like white noise, we could say. Expectation of ut is 0, variance of ut is something sigma square, and covariance between ut us equal to 0 for all t not equal to s. So this follows all the the assumptions that were present in the OLS estimation. However, the error terms that are actually present in the regression model, these are serially correlated. Why? Because the current value at tth term, let's say at time point t, whatever the error is, it is linearly dependent on what the error was during a previous time point. Now, as examples, we can give like prices, stock prices, let's say. So it's highly likely that whatever the price is today or what the price of a stock will be tomorrow, it will be closely associated. It's not exactly independent of whatever the stock price is today, right? So those kind of situations where the current value is a function of the previous error term, those are autocorrelation issues. Now, we talked about the sources of autocorrelation, how it could arise. It could arise because of some omitted variable. It could also arise because of misspecification or specification of a wrong functional form. And then we discuss types of autocorrelation like positive or negative autocorrelation. So, uh, based on these row value, if this row is less than 0, then we say that this is a negative autocorrelation. If row is greater than 0, it means positive autocorrelation. Now, what it means in a graphical sense of the term, if we have this is, let's say, my 0 thing. If we have something like this for a few points where it is the one value of the error term, let's say this is et by t here. So one value of the error term is very closely associated and positively related with the previous error term. So if we have something like this, then we can say that maybe this is a positive autocorrelation. However, if we have repeating or alternating patterns like that some here, then here, then here, then here, like this, if we have alternating things, then we can say that we have negative autocorrelation. Am I audible?
Hello?
Yes, ma'am, audible, ma'am.
Yes, okay, okay. I was just not sure. All right. So, um, one second. Okay, so then we moved on to discuss what could arise as problems due to this autocorrelation. So, the OLS estimates what problems we would face if we use OLS when autocorrelation is present. So, in such cases, even though the OLS estimator remains unbiased, it does not remain consistent. And the standard errors increase. As a result, the confidence interval will be larger and thus incorrect, because the goal is to get precise confidence limits. Okay, we want to be 95% sure that our parameter of interest theta is contained in this within this interval. So we want this interval to be as precise as possible. And if you carefully, if you remember that whenever we were constructing, it would be constructed around some mean and standard error kind of a thing. So if this term increases, then what happens is that this is just for the representative purpose I'm giving. Okay, do not, this is not the form always, so I'll better not write it, but you understood, right? Some expected value plus minus some form of the standard error uh, of the standard error. So if that part increases, then the confidence intervals get larger, and then that, as a result, it might become incorrect, and we would also get incorrect test of hypothesis, because the test statistics or the t statistics specifically for each of the regression equations, like if we have standard error of beta hat, if this term increases, then, or if this term decreases, then we would have something very incorrect. Okay, so this is why we need to first detect, and then because of the consequences of using OLS, because of the grave consequences of using OLS in the presence of autocorrelation, we should somehow correct it and then proceed to our analysis. So in that context, we also discussed the AR1 process. So AR1 model will be something like epsilon t. Let this be my random. So I'm discussing everything in the context of a regression equation. So if I have something like this, epsilon t equal to rho epsilon t minus 1 plus ut, where this rho is my first order autocorrelation. Okay, so this is the AR1 model, and there's another important formulation. I mean, this model can be used in a various contexts, and there is a condition in which this model is this AR1 process is stationary. So I am going to discuss the conditions for stationarity. So what do we mean by stationary process? A process is said to be, okay, I'll write it in a separate sheet. Okay, so a process is said to be weakly stationary if mean remains constant, doesn't change with time, variance remains constant, and the covariance between lagged terms depend only on the lag. So in order to formulate mathematically, if this is my process, then expectation of epsilon t, this should be some constant. Variance of epsilon t should also be constant, and covariance between epsilon t and epsilon s should be some function of t minus s, given that t is greater than s. So this is with respect to some time point I am saying. Let's say t is the third time point, okay? And so to be very correct, I should write this as t not equal to s, and this should be some function of the lag only. Or in other words, if I say covariance of epsilon t and epsilon t minus s, so this should be some function of s. Okay, so this is what the process should. So these are the conditions for stationarity. Now if we have an AR1 model, in order to make it stationary, what conditions should we have? So if this is an AR1 model, now expectation, this one follows all the assumptions. Expectation of ut is 0, then variance of ut equal to sigma u square, let's say, and covariance of ut us equal to 0 for all t not equal to s. So this is following all the assumptions and behaving like the errors of an OLS model. So now if I have to write this thing, expectation of epsilon t equals to a rho of expectation of epsilon t minus 1 plus expectation of ut. So this part will be 0. This one again we can split it into 2. So this we can write as rho into, again putting t minus 1 here, we would have epsilon rho epsilon t minus 2 plus ut minus 1 plus this will be 0. So then this can be written as epsilon square epsilon t minus 2 plus rho u t minus 1 expectation of. So then this part is also 0. So finally what we have is expectation of, okay, so finally what we have is expectation of epsilon t will be expectation of summation j equal to 0 to, I am writing it as infinity, okay, rho to the power j epsilon t minus j, something like this. So all the epsilons are 0, sorry, this into ut minus j. So I'll just recap once more before even taking the expectation. One second. First I'm going to write the expanded form, I think then it will be easier for you to understand. Okay, so if I expand this we can write as rho into, like I said, rho epsilon t minus 2 plus ut minus 1 plus ut equal to rho square epsilon t minus 2 plus rho ut minus 1 plus ut. This one we can write as epsilon cube rho cube epsilon t minus 3 plus rho square ut minus 2 plus rho ut minus 1 plus ut. So ultimately we would have something like rho to the power t epsilon naught plus rho to the power t minus 1 epsilon 1 plus rho to the power t minus 2 epsilon 2 plus so on rho u, sorry, this will be u t minus 2, 1 second. My pen is not working, I'm really sorry, 1 second. Minus 2 u2, this also will be u. And so on, this will be ut. So this thing, if we consider that epsilon naught, expectation of epsilon naught is 0 or some constant mu, we usually take it to be 0. So and also expectation of use are also 0. So then the entire thing, if we take expectation of epsilon t, then it becomes 0, which is constant. Okay. And also if we are,
Ma'am,
yes.
ma'am, in the last slide,
Hmm.
the last term, that is a rho ut. So
Hmm.
I think rho will come, or only ut will come. Rho to the power will
Oh, okay. No,
become zero.
this will become, yes, only ut. I'm sorry.
Only
Yes,
ut.
only ut. So, like
Okay.
I said, we are breaking each of this term into corresponding terms. Okay, and if we assume this thing, then all the expectation of u's will go to 0, and then expectation of epsilon t will also go to 0. Now in terms of if for that a for if we have like, now next we are going to check the variance thing, right? Epsilon t equal to rho epsilon t minus 1 plus ut. So now variance should also be constant. So variance of epsilon t will write as rho square variance of epsilon t minus 1 plus variance of ut, and we also assume that this one and this one are uncorrelated, so there is no covariance term between this term and this term. So now variance of ut, as we had assumed, this one was sigma u square. Expectation of ut was also 0. So now since this is stationary, variance of epsilon t will be equal to variance of epsilon t minus 1. So we can rewrite this as variance of epsilon t equal to rho square variance of epsilon t plus sigma u square. Then variance of epsilon t into 1 minus rho square equal to sigma u square. So we would have variance of epsilon t equal to sigma u square by 1 minus rho square. Now in order, we know that variance should be greater than 0, and that is possible if and only if the rho value is less than 1. Because rho square, then only it will be it will not equal, rho square should always be greater than 0, and it should always be less than 1. Okay, so rho square will always 0 less than rho square less than 1. So the modulus value of rho should also always be less than equal to 1. So this is the condition under which an AR1 process is stationary. If this holds, then only we would have variance of epsilon t equal to some constant, and the expectation will also be some equal to some constant, and the covariance between epsilon t and epsilon t minus k where will be rho to the power k. So if we have an AR1 model, then so to conclude, I am going to write, if I have an AR1 process, okay, epsilon t equal to rho epsilon t minus 1 plus ut, it will be stationary if and only if rho is less than 1. Is it okay? And what do we
Okay, ma'am.
mean by stationarity? Expectation of this will be 0 or some constant. It will not vary over time. Variance of epsilon t will also be some constant, and covariance between epsilon t and epsilon t minus k will be rho to the power k. And this is valid only for an AR1 process. Okay, please be mindful of this. This is only for an autoregressive process of order 1. Alright, so Then we came to how we can detect autocorrelation, and the statistic that we would use is the Durbin-Watson statistic, which is summation t equal to 2 to n et minus 1 whole square by summation et square. Now how are we getting the et's? How to get et? We will regress our response yt on the regressors xt and get the residuals as et. Okay, I'm going to demonstrate how we are getting all of these together. So once we have this, once we have our regression equation, we can calculate the residuals and get the Durbin-Watson statistic. Now if I want you to look carefully into this thing, so et minus 1 whole square t equal to 2 to n by summation t equal to 1 to n et square. And then I want you to remember how should we infer about positive or negative autocorrelation, like intuitively. So you remember the two graphs that we were shown. This is et versus t. Let's say this is for positive autocorrelation. So we would have something like this, okay, a sinusoidal kind of a graph. Okay, and for negative autocorrelation, we would have something like this, alternating patterns, like this. So now you see here, if we have the points lie very close to each other, so the difference between two consecutive points will be smaller. Okay, so if our this dw statistic is small, or I say close to 0, then we would have something like this. Or if I will not write 0, if I'll say if it is small, then we would expect that the square differences are small, means the points also lie very close to each other. So maybe this is a scenario of a positive autocorrelation. But on the other hand, if dw is large, then what it means is that these square differences are large. See, the denominator is constant for everyone. So we are taking differences of consecutive points. So here, if this is the pattern, let us suppose this one is positive, this one is negative. So these differences are way larger. So their square differences will be even more. Okay, so in those cases we can say that, oh, maybe then the errors are negatively autocorrelated. But if d is equal to 0, then we don't know what exactly is happening. Maybe these are all in the straight line, or maybe some are not exactly 0. I would say if it is close to 0, then we don't know what is exactly happening. Okay, or it will be incorrect to say we don't know. We could say that there is no autocorrelation, because the errors are, so when there is no autocorrelation, the errors will be randomly distributed. So if it is closer to 0, we could probably infer that there is no autocorrelation. Now also this was discussed that there is a relation between the Durbin-Watson statistic and correlation coefficient. and the relation is dw equals to twice 1 minus r. So if we look from here, if r is 0 means no autocorrelation, then we would have our d value to be close to 2. Okay, if let's say r is 1, this is strong positive autocorrelation. Okay, and this r I am talking about is the coefficient, is the correlation between this one and this one. Okay, so or rather correlation between the errors or residuals, I would say. So if r is 1, it means there is strong positive autocorrelation. In that cases d will be close to 0, and if r is minus 1, then d would be close to 4, and r minus 1 means negative autocorrelation. Is it okay? So if I draw it to a scale, then this one, if 2 is like 0 autocorrelation in the middle, here we would have 0, this is positive autocorrelation, and 4 would be negative autocorrelation. Now Durbin-Watson also provide critical points dl and du, and based on those we could also take some decision whether what to reject and what to accept. So in a nutshell, if I have to represent something, then we should keep this figure in mind. So let's say this is my scale, this is 0, this is the dl, this is du, here somewhere we would have 2, this is 4 minus du, this will be 4 minus dl, this is 4. So if we have something here in this range, we would say that we have positive autocorrelation. Okay, so here we would support the hypothesis rho is greater than 0. Okay, this will work in this region, whereas this region we would consider, if the statistics fall in this region, then we would support this hypothesis that rho is less than 0. This will be the alternate hypothesis, because my null always is rho equal to 0. So we are going to reject null and conclude H1. Okay, in this region, reject null and conclude. Same here, we would reject null and conclude. If something falls in this region, then we are going to do not reject null. Okay, But if something falls within this region, and one second, I'll draw it in a separate color. So if something falls, let's say, in this region, and if it falls in this region, then we can say that the test is inconclusive. We cannot conclude. Okay, so I'm going to illustrate this with an example. But if the Durbin-Watson critical points are given, then we should test accordingly and look at this picture and do the testing accordingly. Is it okay? Now, apart from this, we also have some assumptions behind using the Durbin-Watson test. The first thing is that it has to be a first order in nature, and the regression model should not include a lag dependent variable as an independent variable. So wherever this is the regression equation from which I am the residuals that I am considering. So it should not include the lagged dependent variable as an independent variable. Okay, so we are normally testing. What I mean to say is that we are testing yt equal to alpha plus beta xt plus epsilon t. This is the regression equation from where we are checking if the residuals are if the residuals are serially correlated. So what we mean to say, this one doesn't have yt minus 1 in the right hand side. So we can use the Durbin-Watson statistic to get the calculations. So as I was saying, we set hypothesis rho 0 versus rho not equal to 0, greater than 0 or less than 0. This is the D thing. And as I was saying, if there is extreme positive serial correlation, D will be close to 0. If it is extreme negative, then D will be close to 4, and no serial correlation, D will be close to 2, like I was mentioning over here. Okay. All right. So then here also sir gave some conditions what to do and what not to do. So just remember this table. So case 2, I've this case 1 and case 2 all have been summarized over here, okay, in this table. So if something is falling within these two ranges, then we are inconclusive. If it is falling within du and 4 minus du, then we do not reject the null and accept that there is no autocorrelation or zero autocorrelation. And if it is in the extreme ends of 2, then we say that maybe there is positive autocorrelation if it crosses dl. And if it crosses 4 minus dl over here, if it falls within this range, then we reject the null and conclude that yes, there exists negative autocorrelation in the data. Now this was all about detection. Now after detecting, then what are we going to do? So here also this relationship that I was talking about, d equal to 2 into 1 minus r, and how we were deriving. So then the remedy is to use a generalized least square. Okay, so then what we are going to do, we are going to lag the original model and get an expression for the lagged error, rewrite it there, estimate the rho using the residuals, and then putting the values of rho here, then we use OLS and get the regression estimates, the adjusted or auto correlation corrected regression estimates. Is it okay? Is it clear? All right. So once this was done, so we also discussed what we mean about multicollinearity, where one explanatory variable in the multiple regression can be linearly predicted from others with substantial degree of accuracy. And then we also discussed the consequences: large standard errors, wide confidence intervals, high insignificant t values with high significant f value, and coefficient estimates will be sensitive to addition and deletion. And the most important thing is, it will be uh, because of these things, it will give good within sample but poor out of sample predictions. So we are fitting a regression line in order to predict what is going to happen in the future, or given some x's, what will be the value of y. So if there's inaccuracy in out of sample prediction, then we should be very mindful about what we should use. And also, as we said, how are we going to detect if there's high pairwise correlation between two explanatory variables, and this one, a high r squared when regressing one explanatory variable at a time on the remaining explanatory variables. This I'm going to explain a little bit more. So I don't know if this concept has been discussed or not. Suppose we have these are my explanatory variables, okay, 1 2 3 4, then this is 4, let's say 4 5, 4 point, let's say 5.5, and let's say 6.7, something like this. So we can see then 20 21 15 27, something like this we have, okay. So if we consider x1 and x2, if we plot a, so here 1 4, 2 5, 3 5.5, this 6.7, something. So we are almost getting a linear relationship based on these things. So the r square between x1 and x2 is going to be high. And as we can see, this one, x1 is approximately equal to x2 minus 3. Approximately, I've constructed this variable. So naturally, x1 and x2 will be highly correlated. So if we find situations where the correlation matrix, so let's say this is the correlation matrix, x1 x2 x3 1 1 1, here we have suppose 0.9 0.9, this one I don't know, maybe 0.2, this one also maybe 0.15. So let's say this is the correlation matrix, the R matrix. So if we find high values, then we should be mindful that okay, maybe these two are highly pairwise correlated. So maybe some problem of multicollinearity can creep in over here. And the next case 2 thing is, we would regress x1 equal to some alpha plus beta x2 plus gamma x3, let's say. So from this equation, we are going to get a coefficient of determination, that is r1 square. So if this is very high, then we can say that okay, maybe this one is like highly, the other it is highly linearly dependent with the other variables. There is also a related concept which is known as VIF, or variance. I don't think this was discussed in class, but still I'm going to share this with you. So if I have to calculate VIF for the jth explanatory variable, this is given by 1 minus rj square, where rj square is the coefficient of determination, that is r square, when we regress the jth regressor on other explanatory variables. So if I take the example that I was talking about, let's say this one, we have x1, x2, x3, something like this. So then regressing x1 on, we would get something alpha to beta 2 x2 hat plus gamma hat x3. So this will be the regression equation. From this regression equation we would get the multiple r square. So let's say that r square value is quite high, 0.86 from this equation. Then the VIF associated with x1 is 1 by 1 minus rj square. So it will be 1 by 1 minus 0.86. So it will be something around like, how much will it be? Can you calculate? So it will be something 7.14.
7.14.
Yes, 7.14. So the threshold or thumb rule, I can say, usually what we do, the thumb rule is, if VIF is greater than 10, then we conclude that there is multicollinearity. Okay, the thing is VIF should be low as possible. If VIF is high, then we conclude multicollinearity. If it is greater than 5, then only we start suspecting. These are like subject to whatever, like interpretation and how much threshold you want to take. The thing is, we don't want any variable in our model whose VIF is high. Okay, so then we would go take corrective measures, either dropping variables or doing some kind of transformation or something else, centering. Sometimes we do centering of the data set, some kind of corrective measures we take, so that the variance is not, so that the VIF is not too high. Okay, so that was one other measure why this high r squared is like taken as an evidence of multicollinearity. Okay, is this clear?
Yes, ma'am.
Okay.
Ma'am, in previous one, ma'am, slide.
Okay.
Okay, previous slide.
Hmm.
Ma'am, one more. Here you, ma'am, here you have written x1 is equal to x2 minus 3. So, ma'am, this 3 came from where?
So while I was doing it, you see, if you add 1 plus 3 4, 2 plus 3 5, so I am just constructing it in such a way, just as to illustrate my point. Like if this is increasing, this is also increasing. If I do x1 equal to x1 plus 3, then there will be exact multicollinearity. Then the problem is, like, if you remember the model matrix that we have, the intercept term will have all 1, and then this one will also have these. If x1 and x2 columns are exactly linearly dependent, then we will not be able to get a unique inverse. We wanted this one, right?
Okay.
Okay, so in order to compute this inverse, it is very important that the rank of the matrix is exactly equal to the number of parameters that I'm going to estimate. If two become exactly linearly dependent, then I am not going to get a unique inverse. Inverse of this matrix will become problematic. So even if these are, so what I wanted to say is that even if they are not exactly equal, they could be very strongly linearly related, and in those situations the pairwise r squares will be high. Okay, this is just an arbitrary term that I used, like I constructed the variable in such a way so as to demonstrate that how high the x1 and x2 can be. Okay.
Okay, thank you.
Okay. All right. So then we also discussed about the parameter stability and structural break, like what happens if we have a situation like there is a natural break in the data set. Somewhere the data was going like this, suddenly there's a pandemic, and then it falls or something like this. Okay. So in order to check if there has been a structural break because if I fit a straight line equation without keeping this in mind, then my line will be somewhere like this, and this could be incorrect. So it is then, in that situation, it will be better to fit some before after cases. Before the regression was this, after the regression is this. So in order to test whether there has been any structural break in the time series or in the data points, we do this chow test, and I think I'm going to do and show you an example with which we'll be able to discuss more. And also we talked about the dynamic modeling and how we can fit an auxiliary regression. So what in case of a dynamic model, what do we do if we have a simple autoregressive model? So we obtain uh, from this AR1 model, AR1 regression, we obtain the OLS residuals, and then we add another term, like we add beta 4 epsilon residual t minus 1 to this equation, and then from that equation we calculate the r squared values, and then multiply it with t, and then check if in large sample with chi-square 1, and then if the value exceeds chi-square 1, then we are going to reject h naught. Also we learned something about Granger causality. So Granger causality means that one time series is consistently and predictably changing another time series. So first we fit yt on the lagged values of yt and the lagged values of the regressor xt, and then we jointly test for the coefficients of the xt terms. So this also we do as an f test. So how do we do it? So first is like yt equal to, if we write the model, yt is based on, let's say, p lagged values of yt plus yt minus 1 plus vp yt minus p plus gamma or alpha 1 xt minus 1 to alpha p xt minus p, let's say. So this is my unrestricted model. So if I fit this unrestricted model, so from here I'm going to get a residual sum of squares. Okay, so that will be my URSS, and the corresponding degrees of freedom will be the total number n minus the number of parameters that I am going to estimate. So here I have p parameters, here also I have p parameters and 1. So we have 2p plus 1. This will be the degrees of freedom of the unrestricted model, and the restricted model will be alpha 1 equal to alpha 2 equal to alpha p equal to 0. So we are having here p restrictions. Okay, p alphas all are set to 0. So then we'll fit yt equal to beta naught plus beta 1 yt minus 1 plus beta p yt minus p. Okay, from this model we are going to get a restricted sum of squares, and once we get the restricted and unrestricted sum of squares, we are going to do that. So this will be restricted minus unrestricted divided by p by unrestricted sum of squares by n minus 2p plus 1. And then if f observed is greater than fp n minus 2p minus 1, then only we are going to reject h naught and conclude that yes, the then we'll conclude that x Granger causes y. Okay, so this is the test of about Granger causality. Is it clear?
Okay.
Okay. So then we also spoke about some spurious regression where the x's and y's do not make any sense. Nevertheless, they have high R square and a low Durbin-Watson statistic. So we have to be mindful of such cases as well. And then, as I was saying, we were talking about stationarity. I discussed the conditions. So the mean will remain constant over time, variance is constant, and correlation coefficient between any two pairs depends only on the length of the lag and not other variable. So if this is not met, then we can call any time series as non-stationary, and in order to achieve stationarity, we can do a lot of things. We can also we can take natural logarithms, we can fit trend lines, subtract that or remove that trend component, use differences, and then we can achieve stationarity. And this is the first order difference. Differencing means taking differences between consecutive terms. Differences between consecutive terms. Okay, and then we had some uh, definitions about stationarity. So these are the expressions which we should keep in mind. Okay, because these calculations will become necessary. Suppose if you are given a formula for yt and you've been asked find out if it is stationary or not. So in order to find out stationarity, these are the conditions. If the mean is some constant, if variance is also equal to some constant, and the covariances depend only on the lag between two variables, then only we can call the processes stationary. Okay, and then we also talked about fitting the autoregressive models, and when we have non-stationarity in the data, so the first step is to do some transformation or some order differencing and get a stationary time series, and then evaluate based on the ACF and the PACF graphs what will be the order of this PDQ. Okay, so this is how we should follow. I think in the R session I'm going to show how we can do this modeling. And also, if we have to go for unit root testing, we should go for the two tests that were discussed, Dickey-Fuller and augmented Dickey-Fuller test. Okay, so this is what the test is all about. We use the augmented Dickey-Fuller if we suspect that there is autocorrelation in the residuals, but it includes the lags of residuals too. And if we run it with a test, and if it still shows the unit root, then we conclude that the difference is stationary. Okay, so what we test is that we test a difference series on its previous lags, and we test for this term delta equal to 0. If delta equal to 0, then we conclude that this is non-stationary, but if it is not equal to 0, then we conclude that this is stationary. Okay, the difference is stationary. So if you are asked that how to check what are the errors in what are the tests in a time series modeling to check whether there exists any unit root or not, then the answer will be the Dickey-Fuller and the augmented Dickey-Fuller test, and the difference being that the lag in the augmented Dickey-Fuller test we also include the lags of residuals. Okay, and then the ACF is so I'm going to tell you what we do. So if I have a covariance between, let's say, this one and epsilon t minus k, this is equal to, for an AR1 process I'm telling, okay, so this will be rho to the power k, something like this, and the variance between epsilon t and epsilon t will be something, okay, let's say here they have represented it as gamma naught, so I'll represent it as rho naught. So then if I take correlation between epsilon t and epsilon t minus k, this is only what we say is gamma k by gamma naught according to their notation. So this function is my autocorrelation function. So when I'm doing a plot, what I'm actually doing is it at lag, these will be my lags, okay, and here I am plotting the ACF. So this one will be the value of the current time point with the previous time point. Here I'll have the value of correlation between current and 2 time points backwards. So this is how the ACF is getting calculated, that is the autocorrelation function, and the PSCF will give a partial correlation of a stationary time series with its own lagged values and is measured by the partial covariance. So if we regress the current series and the at time points, what I mean till like if till this we do, if theta k is also significant, then we say that the series will have a kth order of autocorrelation. Okay, so there are ways from which we can find out the whether it's a moving average process or the autocorrelation process. So for an AR process, the sample ACF will damage exponentially, and the lag will be determined when we have some spikes on the PACF graph. So let's say this is we have a graph like this. So this is an ACF where it is like decaying like this, okay, we have something like this, these are the lags, and this is the ACF autocorrelation function, and so it's not represented in that way, it is represented at spikes, okay. So here we have something like this, and the PACF, let's say we have 1 2 3 4, and this, let's say this is the line of significance that is given as output from any of the softwares. So here in such a case we see 2 spikes. So if we have an ACF which is gradually decreasing and PACF showing 2 clear spikes, we can say that this is an autoregressive process of order 2. Similarly, if we have an ACF where it is like decaying gradually and the ACF is decaying gradually and the PACF, let's say this is the line of significance that has been given, and we have something like this. So maybe this is an AR3 process because we can see 3 clear spikes. Okay, now in most of the real life situations it will not be as clear as this one, so then you might have to take a call. Okay, and for the MA models, the PSCF will see gradually, it will go away gradually, and you will have spikes in the ACF curve. So if I say this is my ACF function, and these are the lines that have been given. So if I have 1 2 and then something like this, and the PSCF is like gradually decreasing, so maybe this is an MA2 process, moving average order, a process of order 2. Okay, or if we have one very prominent spike here at lag 1, and this is gradually dampening, so then this is maybe a moving average process of order 1. But if we have a combination of both, then if it is, let's say we have a combination of both, the ACF is also showing spikes, the PSCF is also showing spikes. One second. So if we see that the ACF is also showing clear spikes and then diminishing, PSCF is also at lag 1, PSCF is also showing clear spikes and then diminishing. And if it is not a differenced, the series is actually as it is, it's not differenced, then maybe we would go for an ARIMA 101 fit. But if this pattern is observed for, let's say, delta YT, then we would go for an ARIMA 111, something like this. Okay, is the idea clear how graphically we can look and conclude? Any doubts? Okay. Okay. So then lastly we also discussed something of related to co-integration, where two or more time series move together in an equilibrium relationship. So they are said to be co-integrated if they are integrated of the same order, that is they have the same like if one is different series, the other is also a different series, and there exists a linear combination that is stationary. And we also proposed there is also an error correction mechanism that was proposed, where this term is that error corrected thing, where this occurs when there is a shift from that equilibrium modeling. So here we have described how to do those, get the fitted values, and then applying the correction term, getting an estimate of gamma, we can use this corrected model and get the estimates of the coefficients. So these are like advanced topics which if you are interested you can look into. Okay, so with that I'm going to move on to the problems that would be worth discussing, that might come in the assignments and questions. So the first one was this: which of the following is an indicator of negative autocorrelation? So the answer would be negative autocorrelation. So we would have something like this. An alternating pattern in the residuals. So if I draw a scatter plot of, let's say, the tth time point, and this is my t minus 1, we would have something like this. Okay, a negative thing. if this is a linear regression. And if I plot the residuals with respect to time, then we would have an alternating pattern in the residuals. That would be indicative of negative autocorrelation. Okay, as it was discussed over here, you see we have some negative pattern, something like this. Is it clear?
Yes. Okay, ma'am.
Okay. Okay, so then question number 2. We consider the following AR1 process with the white noise error term, this such that this is the modeling. So the unconditional mean of y will be given by. Now, the first thing we should note is that here the mean of y is not having any tth term. So we have to check if this thing is stationary or not. So if you remember, yt equal to 0.8 plus 0.6 yt minus 1 plus ut. So this is the autocorrelated term. Okay, so this is less than 1. So we can say that okay, this is a stationary process. So expectation of yt equal to 0.8 plus 0.6 expectation of yt minus 1 plus expectation of ut. Okay, ut follow IID with mean 0, variance sigma square. So expectation of ut will become 0. And since this is stationary, so this is stationary. Okay, so this thing we can write as expectation of yt equal to 0.8 plus 0.6 expectation of yt. Do you agree? Because stationarity means that the mean will remain constant over time. So the mean of this series yt and mean of yt minus 1, both of them will remain the same. Okay, so if we move this one to that side, so then expectation of yt would be 0.8 divided by 1 minus 0.6, 0.8 by 0.4, which is 2. So this is the correct answer. Is it clear? Alright, so I'll move on to the next one. Here again, the unconditional variance of AR1 process is given by, so it was yt equal to 0.8 plus 0.6 yt minus 1 plus ut, where ut follows IID 0 sigma square. So variance of yt will be variance of constant, doesn't make any sense, which will be 0. Variance of 0.6 yt minus 1 plus variance of ut, and we have this assumption that these are not correlated with yt, so we will not have any covariance term. Now this one we can write as 0.6 square v of yt minus 1 plus v of ut. Why? Because variance of ax can be written as a square into variance of x, where a is some constant. Okay, so variance of ut is sigma u square, and since this process is stationary, variance of yt equal to variance of yt minus 1. Therefore, what do we have? Variance of yt equal to 0.36 variance of yt plus sigma square. So then we have variance of yt equal to sigma square divided by 1 minus 0.36 equal to sigma square by 0.64, which is equal to 1 point, and this is the answer, 1.5625. So the answer is this one, 1.5625 sigma square. Is it okay?
Okay.
Any doubt? All right. All right. Then we have this question. So we consider this model yt equal to alpha plus lambda t plus ut. So which of the following best describes the process for yt? So here, this, is it a stationary process? First we are going to check that. Expectation of yt equal to alpha plus lambda t plus expectation of ut equal to alpha plus lambda t. This depends on t, therefore not stationary. Is it clear? So this is not stationary. Is it a unit root process or a random walk with a drift? No. Why? Because in both scenarios we would have lagged terms on RHS. So in case of random walk, what do we have? Yt equal to yt minus 1 plus ut, something like this. In case of unit root also. So unit root, what do we test? If we have some phi yt minus 1 plus ut, if phi equal to 1, then we have the random walk or unit root. Okay, but since we do not have lag terms on the RHS, this is not a random walk with drift, so with drift would mean mu plus something. Okay, so this is not a random walk with drift, it is not a unit root process, but it is a deterministic trend process. Why? Because t is this ft equals to lambda t. So if we have a trend equation like this, which is deterministic. Okay, so that is why the answer will be, this has a deterministic trend process. If we have something like t square, then that could be a quadratic trend, because the trend component is being modeled over here. Is it clear? Is it clear? Okay, thank you. All right, moving on. So here we have a question that suppose a researcher wants to test the structural stability of the following model. The total sample of 300 observations are exactly split in half of the subsample regressions. What would be the unrestricted sum of residual square for this test? So this test, that is F chow test, is actually equal to that restricted versus unrestricted test. Okay, so if you remember, this is the restricted sum of squares from combined model minus residual sum of squares due to residual from the subcomponents divided by k by SSR1 plus SSR2 divided by n minus, n, instead of n we have n1 plus n2 minus 2k, where k is the number of parameters. Be careful, not regressors, number of parameters to be estimated. Okay, so then if you move it into that unrestricted versus restricted framework, what we have is that here he would have the restricted sum of squares minus unrestricted sum of squares by number of restrictions by unrestricted sum of squares by the df. So if we compare, then the unrestricted sum of squares will be the sum of the residual sum of squares from the first and second sample regressions. And the logic is that if I do like a comparison between the two test statistics, then I am getting it that way. But that is not exactly the correct thing to do. The correct thing is why is it so? So the unrestricted sum of squares, so here what we should remember is that we should remember the context. So we have already split. Okay, so we have already split it into two samples, let's say S1 and S2. So we have this regression where we have this one and we have this one. Now this is under no restrictions. When we are restricting ourselves, that let's say this is y1 equal to alpha naught 1 plus beta naught 1 x1, and let's say this is y1 equal to y11 equal to alpha naught 2 plus beta naught 2 x11, something like this. Okay, so the under the restriction is that alpha naught 1 equal to alpha naught 2, beta naught 1 equal to beta naught 2. So under the restricted model, what we are doing, we are, even though we have this kind of a line, we are fitting this line, a straight line, for all the samples. Okay, so the context is that when we do not have any restrictions, we are fitting two models separately. Under restriction, we are fitting one model. So that is why the under restriction, the unrestricted sum of squares will be the sum of squares of errors when we are fitting these splines in parts, like these regressions in parts. Okay, that is why the sum of squares unrestricted would be the sum of the residuals that we are getting, sum of squares residuals that we are getting from the subsample regressions. Is it okay? All right. So here we have that suppose the RSS from first subsample and second subsample and whole sample are these and these, then what is the value of F chow statistic? So then F chow will be, so before going to that I'll just rewrite the model over here. So we have beta naught, beta 1, beta 2, three parameters. Yt equal to beta naught plus beta 1 x1t beta 2 x2t, x1t plus beta 2 x2t plus ut. So here how many, what is the value of k? K will be, what do you think, what will be k? Anyone? Will it be 2 or will it be 3? Just tell me this one.
Three.
Yes, it will be 3 because we are k is equal to number of parameters estimated. Okay, so now the F chow will be the restricted sum of squares errors minus restricted sum of squares from one sample, sorry, sum of squares error from one sample, sum of square from 2 divided by k by SSR1 plus SSR2 divided by N1 plus N2 minus 2k. Okay, this was the chow statistic if I remember correctly. T1 plus T2 minus 2k. Yes. So now we'll just substitute the values. So this will be the restriction. So under restriction we are fitting just 1. So this will be the value 166.4 minus 81.8 plus 72.6, everything divided by 3 by 81.8 plus 72.6 divided by, okay, N1 plus N2, how many did we have total? 300 observations. So that will be 300, or we split it equally, so I'll write 150 plus 150, it's actually the same thing, minus 6. So what will be the value? Can you calculate? So this is 166.4 minus 154.4 by 3 divided by 154.4 divided by 294. So this will be 7.616. So the answer is A, 7.6.
.6.
Okay. Okay, so I think there is no doubt here. So we'll move on to the next one. Okay, so here I have a variable x and y. We have been asked to fit a model of y on x and see if the residuals are serially correlated. We have to calculate the Durbin-Watson statistic and comment. Okay, so we move on to this one. So like if you just fit an OLS y equal to alpha, or let's say beta naught plus beta 1 x plus epsilon, this is my OLS model. Okay, so if I have to do beta naught hat, it will be y bar minus beta 1 hat x bar, and beta 1 hat will be summation xi minus x bar yi minus y bar by summation xi minus x bar whole square. Okay, so we can easily use these formulas to calculate beta naught hat and beta 1 hat. So using this, we would get beta naught hat to be 1129.225 and beta 1 hat would come out to be minus 2.627. Okay, so then the fitted equation is y hat equals to 1129.225 minus 2.627. Okay, so you can check it. Now we have to find out the Durbin-Watson statistic and do a comment. So how am I going to do it? So here I'll do one thing. I just copy this table. Okay, now here I have already obtained the regression equation. So the regression equation is what is wrong? One second, my pen seems to have. Alright, so I have my equation as minus 1129.225 minus 2.627x. So if I calculate y hat from here, I would get this to be 1129.225 minus 2.627 into 10. So this would be 1102.9577. Similarly, I can calculate 1.29.225 minus 2.627 into x, that is 20. So this would give me 1076.6901. Similarly, I would have here 10. You can check, okay, if the values are matching. This will be 1024.1549. This will be 997.8873, and this would be 1011.0211. So we have the y predicted values over here. So once we have the y predicted values, we would take the residuals, okay, or the e values. So how will we calculate e? We will get y minus y hat. So then this will be 1100 minus 1102.9577. So we would have minus 2.9577. then we would have 123. So if I write it afresh, okay, 1 second, I'm going to copy it. Okay, here I'm going to write it afresh, these two. Okay, so the y hats were so this was 1102.9577 and this was 1076.6901. Okay, this was my y hat. Okay, so then I would get the residuals. That will be this will be y minus y hat. So here I would have minus 2.9577. This would be 123.3099. This will be minus 52.2887. This would be minus 274.1549. This will be 217.1127 and this will be minus 11.0211. Now these are the EIs that I have. Then I have to calculate ET minus 1. So this will be minus 2.9577. Sorry, this one minus this one, like this we have to go. Okay, actually it's the same thing because anyway we are going to square it up, but still. So here we will have like 123.3099 minus of minus 2.9755 sorry 9577. So here we would have 126.2676. This will be minus 175.5986. Then we would have minus 221.8662. Here we would have 491.2676. This minus this would be minus 228.1336. Okay, so now we have the residuals and the ET minus 1 things. So now in order to calculate the Durbin-Watson, what we have to do, we have to take a sum. We have to first do this square by summation ET square. So we'll square each of these terms, okay, and then add it up. So 2.9, so almost 3, this will be something close to 8 point something. Okay, then this one square it up and then add. This one also we are going to square it up and then we are going to add. So I'll again draw the same thing. Okay, so here now we have these values. So we already have the residuals, ET and ET minus 1. So from this one we would get the ET square, which will be minus 2.9577 whole square. This will be 123.3099 whole square, and so on and so forth. This will be squared, and this column again we are going to square. So this will be 126.2676 whole square minus 175.5986 whole square, and so on. Then we are going to take a summation of this column and this column, this one and this one. This one will be the denominator and this one will be the numerator. Okay, so after all of this, we would have the Durbin-Watson statistic as Et minus 1 whole square by t will be from 2 to n. This is Et square t equal to 1 to n. So then we would get the values like the numerator will be 389391.8 and the denominator will be 140,368.5 and the statistic value would come out to somewhere close to 2.774069 something, approximately equal to 2.77. Now you remember that flag which I was showing, what to do in case of this. So this is 0, this is 4, this is 2. So this one is highly negative autocorrelation, this is highly positive autocorrelation, and somewhere here we would have dl, we would have du, here we would have 4 minus du, and here we would have 4 minus dl. So now our is 2.77, so it might fall here, it might fall here. So now we are going to get this Durbin-Watson statistic table. Okay, so here for this table, k is equal to number of regressors or number of predictor variables. Okay, so this will be parameter, number of predictor variables except intercept. Okay, this is very important. Here whatever we have, that is without excluding the interceptor. So here we have x and y, so we have only one predictor. Okay, and the OLS model that we fit was beta naught plus beta 1x plus epsilon. So here k will be equal to 1 because we are not including the interceptor. Is it fine? And n is the sample size. So here n we have 6. We took 6 observations. 1, 2. Okay. So for the sixth one, dl is 0.61, du is 1.4. So this is 0.61, this is 1.4. So 4 minus du will be 2.6 and 4 minus dl will be somewhere close to how much? 3.4 minus 0.61. 3.39, and our dw is 2.77. So as we were saying, this one is positive. We should if it falls here, then we would say that reject H naught, no autocorrelation, and conclude positive autocorrelation. This one, if it falls, then we'll conclude no autocorrelation. Sorry. Okay. So if it falls here, then we say no autocorrelation. And if it falls, so here our test statistic is falling 2.77. And here if it falls in this range, then we would reject H naught and conclude negative autocorrelation. So since our and this stretch and this stretch, those were inconclusive. So since our statistic is falling here, we don't know what to do. So our decision is inconclusive. We cannot reject or accept the null hypothesis with this variable. Is it okay?
Okay.
All right. So here I have another question based on the multicollinearity. So we consider a multiple linear regression with k minus 1 regressor variables. If there is a strong multicollinearity between xj and any subset of k minus 2 regressors, then variance of beta j will tend to how much? So what happens when we have such things, okay, such so variance of beta j in the presence of it becomes 1 minus, sorry, it becomes sigma square by 1 minus rj square. Okay, this will be beta j. So here as rj square increases, their strong multicollinearity means rj square will increase. So it will move towards 1 because the multiple correlation coefficient will always range between 0 to 1. So this one, as there is strong multicollinearity, this one will move closer and closer to 1. As a result, what will happen? The denominator will move towards 0. And as a result, the variance of beta j will move towards infinity. Is it okay? So this is why this term is called a variance inflation factor, because it is inflating the variance. Is it clear?
Okay.
So again, what does autocovariance measure? So autocovariance measures that covariance between two points of same series. So we are observing the same series epsilon at two data points at two different times, and then taking the covariance or the linear dependence, because if you remember, covariance, correlation, they all measure a linear relationship. Okay, so this autocovariance is a measure of linear dependence between two points on the same series observed at different times. First thing is it is a linear dependence. So A, C and D. Multiple points, it could be between multiple points, but covariance usually we take pairwise between 2 points. So then this is getting cancelled. It's not between multiple points, it's between 2 points. Covariance between x and y. Always we have heard of that. Okay, and then is it same series or different series observed at the same time? No, because it is auto, it means same series but observed at different time points. I hope this is clear. Okay. So the next one is, which of the following is not a necessary condition for weakly stationary time series? So to be very specific, weakly stationary or a stationary time series means mean is constant and does not depend on time. This is a required criteria. Autocovariance function depends on S and T only through their difference, where S and T are moments in time, because it depends only on the lag and nothing else. So this is also a required criteria. So the time series under condition is a finite variance process. Of course, because we when we were, you remember when we were doing that conditions for an AR1 process, we set rho, we got something like 1 minus rho square. So we set rho less than 1 so that we would have a finite and constant variance. Okay, so the time series should have a finite variance process. So then all these are necessary conditions. Which is not a necessary condition? That the time series is Gaussian. We did not make an assumption about whether the epsilon t's or the yt's are following a normal distribution. Gaussian means normal distribution. So the answer is D. D is not necessary. Is it okay?
Okay.
Okay. Now, question number 11. So, the diagram shows how the scatter plot of stock prices varies with number of days after general election. So, this is day 1 after general election, day 2, something like this. Okay. So, here if we see, till here we have a specific trend. Okay, it's moving upward. It's like a linear trend. Somehow after here, the line seems to have shifted. So this looks like fitting two splines would be greater. There is some structural change in the relation of the thing. So we have to see if it has changed after the 10th day. So what we are going to do, we are going to split this with respect to x and y equal to 10. So here we have been asked to divide equally into groups. We will do that. We will divide equally into groups. So this will be my group 1, this will be my group 2. Okay, so then fitting y on x from this table, from table 1, I got ss1 as this one. ss1 is the residual sum of squares. Okay, from ss2 the residual sum of squares is this, and if we combine the restricted sum of squares due to residuals is 552.57 when we take all the variables together and then we do perform a regression and get the sum of squares. So then what test we are going to do? We are going to do the Chow test. So it will be, so what will be this thing? This will be 552.47 minus, we'll add these two up, 32.53 plus 25.776. The entire thing we are going to divide by number of parameters. So how many what should we divide this by? We are fitting y equal to beta naught plus beta 1x plus epsilon. So what should be k? K should be 2. So we'll divide this by 2 by again 32.53 plus 25.776 divided by n1 plus n2 is 30 minus 2k is 4. So the value of the test statistic will be 110.17. Now this one we should compare it with an F statistic. So what will be the df of the F statistic? The numerator degrees of freedom will be this will be the, whatever we are dividing it by, that will be the df for the numerator, and whatever we are dividing in the denominator, that will be the df for the denominator. So here we would have f2 16 and the point is 0.05. So this is the column for f2 and this is for not 16, 26. 30 minus 4 is 26. Okay, so here we would have this is the segment that we should be considering. So for 0.05 we have 3.37. So f critical value is, f critical value is 3.37 and f chow is 110 point, how much did we get? 110.17. So our decision will be what? We'll reject null and conclude that there has been structural changes, or in other words, alpha naught 1 not equal to alpha naught 2 and beta naught 1 not equal to beta naught 2. Okay, is it clear?
Okay.
Okay, so with that I'm going to end today's session. If you have any queries, you can tell me. Anything else you have? Yes.
No, ma'am. Thank you.
Okay, thank you. All right. Thank you for joining and I'll see you next week. Bye bye.